Good evening, everybody. Tonight we can welcome our first guest speaker from Sweden. Though I'm not actually sure whether you were born in Sweden. Are you German by any chance?
Yes, yeah.
I thought as much. So, Professor Alex Hagermann. Axel studied geophysics and planetary physics in Karlsruhe, I think that's correct, and Münster in Germany. And after a JPS, which is the Japanese Society for the Promotion of Science, postdoctoral fellowship at the Institute of Space and Astronautical Science in Japan, supported by the Alexander von Humboldt Foundation, he had a brief stint as an instrument manager on the European Space Agency Rosetta space mission, based at the University of Cologne. In 2004, he moved to the Open University as part of the Cassini-Huygens team, investigating Saturn's moon Titan. Axel has since been working on the analysis of space mission data and supporting science, and in 2018, he joined the University of Stirling, from where he moved on to Luleå, is that correct?
Luleå
University Space Campus, can't say it, in Kiruna, Sweden. A suitable geographical location for his main interest in ices. Axel is a particular interest in the thermophysics of ices and regolith, preferably a mixture of both icy regolith. He also likes ice cream. So can everybody please welcome, in the Mexper & Swinton Astronomical Society way, our speaker for tonight. Thank you, Axel.
Thank you, everybody. Now, I just need to check, which county am I in? Is it South Yorkshire?
It is South Yorkshire.
The Republic.
That's good, because obviously I didn't have to travel, but it's lovely to be in the county right next to Paradise. So thank you very much for having me. I think when I signed up for this, my whereabouts this year were somewhat unclear. I was supposed to come down from Stirling, which didn't happen, obviously. Now I need to share my screen now, apparently. So
okay, we can see your screen.
Okay, and can you see it in its full glory now?
We can.
Oh, fantastic. Okay. My talk is about my main interest in space research, which is ices. As is obvious from my CV, actually, I'm not an astronomer. My background is geophysics, which is why my main interest is on physical processes in our solar system rather than beyond. That also lines up with my other main interest, which is ice cream. So regolith, by the way, that's basically soil on other bodies in the solar system. We speak of soil generally when there's been some kind of biogenic activity. And if there is no biogenic activity, then obviously or biogenic alteration, we talk of regolith. So for instance, the moon has regolith, as has Mars. This icy regolith stuff that is actually something that interests me. And basically, I just call it ice and rocks in the solar system most of the time, even though the rocks can be fairly small. Now, why are ices so interesting? They're found almost everywhere in the solar system. We've got them on Earth, we find them on Mars. On the Moon, we probably have ice. Entire outer solar system is full of it. Ices are also very, very important as drivers of physical processes. They control planet's climate. Earth's climate, ices change our planet's albedo quite dramatically. Ices are what drives the activity of comets, and they also help provide an environment supportive of life, for instance. That is something that we can see, for instance, in the icy moons of the outer solar system. Ices are still poorly understood, though, because we don't quite understand how some landforms on Mars come about, because carbon dioxide ice on Mars is nowhere near the triple point. So actually, we do not have liquid carbon dioxide. Then we don't quite understand how comets can be hard and soft at the same time. We also don't quite know what makes asteroids stick together. Some of that might have to do with ices. And when I talk of ices, I basically mean sort of any volatile substance. You know, ices can be water ice, carbon dioxide ice, methane ice, and so on. And the two ices that we mostly investigate in my group are water and carbon dioxide ice. And now, what do we do with these ices? I mean, our research, we do nothing to do with telescopes. Actually, it's purely environmental research, purely experimental research. It's simulations in the laboratory. So we simulate the environmental conditions on Mars or on comets or on asteroids. We can also do random cold places on Earth. I mean, that is not a big challenge, obviously, because Mars is a lot colder, atmosphere is a lot thinner. And what is sort of unique about the activities that are going on in my group is the scales. So we work on samples that are about this size, yeah. So something smaller than a football, basically. And this research we do to underpin theoretical models, to explain spacecraft data, and basically it is to bridge the scale gap between the actual physics, where people investigate sort of molecular processes, to the remote sensing activities that are going on in space science. So imagery taken from spacecraft of planetary surfaces. And how do you create these planetary environments in the lab? Well, you need a vacuum chamber for most places in the solar system. Mars, effectively, I mean, the atmosphere for all practical purposes, almost vacuum. Then you need something to simulate the atmosphere, which is why we've got this carbon dioxide gas line going into that vacuum chamber. We need to cool it. I mean, the only way to cool something down to like minus 140, minus 150 Celsius is liquid nitrogen. So something that we usually have lots of fun with is like large tanks of liquid nitrogen. It can do fantastic things with it, such as, for instance, make ice cubes really, really rapidly for your gin and tonic in case you run out. So then we use some other kit that is quite unique to this particular kind of science, because these scales are so unusual. We have got very unusual suppliers. So our key equipment is environmental chambers. We've got a solar simulator, which is basically a massive lamp that very high power, instant sunburn. It gives you. We've got several freezers at various temperatures. We use lots of liquid nitrogen, but other key suppliers, surprisingly, are IKEA, where we've bought stuff. B&Q for the UV protection that you can see there. This UV protection here. Can you see my mouse pointer, by the way?
We can.
Okay. So this fantastic UV protection was bought by my PhD student. She obviously went down to B&Q, and I think she chose well. Another supplier when I was still with the Open University was Milton Keynes Snow Zone, because unlike Kiruna, where I am now, snow was quite hard to get in lovely Milton Keynes. So we had this agreement with the Snow Zone, which is an indoor ski center, that we could just come there and basically fill a large styrofoam box with snow in the snow zone, and then just put it into the car boot and drive off. So that was really, really nice. We also were offered free skiing, which was even nicer. Now, I talked about ices in the solar system. So I'll take you on a quick tour. We are here, and we'll start on Mars, so a bit further out, and then basically we'll take a bit of a detour. I won't talk much about Titan in this talk, but I will tell you a bit about Comets and the Rosetta mission, and also the recent Japanese mission to a comet. So to an asteroid. So what is interesting about ices on Mars? Well, on Mars we've got polar caps very similar to Earth. Mars is very interesting because it might actually offer us insights into what happens if things go wrong with the climate. And I think that's probably what's going on Earth right now. I mean, we see massive climate changes. And we know from Mars' current geology that in its history it must have looked very, very different. And the atmosphere must have been a lot denser. There must have been a lot more water, and it's also quite clear that in the past it was also a lot warmer. So we can see carbon dioxide ice and water ice on the Martian surface. We've got two polar caps, northern and southern. The northern polar cap is covered by carbon dioxide ice, evaporates during the summer season. But then the base is many water ice. The southern polar cap is a perennial and seasonal carbon dioxide cap. So these ices in the polar region of Mars, they're linked to the most active geological features on the Martian surface. And that is actually shown by the dark deposits that we see in the imagery and by how quickly they change. And one of the surface features that has been puzzling people's imagination for quite a while are these so-called spiders. Now, most of us are old enough to remember, David Bowie's Spiders on Mars, and these spiders really exist on Mars. It's landscape features that were dubbed spiders. We've also seen some permafrost features. Now, spiders on Mars look like this. I don't know how many of you have actually seen images of this, and whether many of you actually are interested in planets and geological features on them. But that nickname was given to them, I think, a bit less than 20 years ago, and they're negative topographical features. That means these are little troughs and depressions, and in the middle there's this sort of crater, and they occur in groups, and sometimes they overlap. The central depression of these things is usually like in the tens of meters range, so like 50 meters or so. And the entire thing is about between 100 and 300 meters wide. So that's the Martian spiders for you, and they look odd. And another thing is their production process, and the way they form is also rather odd. Now, we have seen carbon dioxide ice and water ice on the Martian surface. So it probably has something to do with ice evaporation, and spiders in this region, because called cryptic region, cryptic because there are so many strange landforms in there that somebody dubbed the entire region on Mars cryptic region. So we think these features form when carbon dioxide ice sublimes or sublimates, and when the pressure of the gas below the ice exceeds the ice strength, which then ruptures the ice. So you would think, why would that happen? And the reason for that is sunlight impinging on the ice cap. And carbon dioxide ice has this really strange feature that actually it is almost transparent to most wavelengths. So you can actually have a body underneath the ice or embedded within the ice that absorbs the sunlight, and that then gets hotter than the actual surface. So that is something we do not really get on Earth. I mean, on Earth, basically, whatever is exposed to the sun gets hottest, and below the surface, most of the solar has been absorbed already. Now, so we think actually this has something to do with the optical properties of carbon dioxide ice, with the fact that we've got sort of the bottom of the ice where the sunlight then hits the regolith, that means the soil of Mars, this getting hot. That means some of the ice sublimates, and that means in turn that the pressure underneath the ice rises. And the idea for the formation of these things is that at some point the pressure rises so much that the ice cracks and the gas escapes. And as the gas escapes, it entrains a lot of the sediment underneath the ice and takes a lot of dust with it. So that is the model, and people have been, creating mathematical models. I mean, first of all, geologists always come up with these so-called conceptual models. They say this is the process, how this happens, but they've got no sort of physical, actually, estimates of the orders of magnitude of the forces going on there. So they propose a process, and then physicists come about and try to do a model on this. So basically, they go about and go, okay, we do some fluid dynamics, and then finally, somebody tries to prove this supposed process in an experiment. And because it's quite difficult to simulate Martian conditions over scales of like 100 to 200 meters, you had to limit somehow the size of these experiments, the size of the samples. So this is the effect of solar radiation on this carbon dioxide ice on Mars. And this lovely cartoon was drawn by the same PhD student of mine who selected the UV protection at B&Qs. So she's drawn this lovely cartoon showing that some of the solar radiation, when it impinges, is reflected. Then most of it actually penetrates into the ice. You've got some of the ice being warmed up and heat escaping as infrared radiation. But interesting things happen when you've got an absorbing layer, because that warms up, and then around this absorbing layer, you've possibly got sublimation of the ice. Dark particles, same thing, and anything that happens below the ice obviously has to be warmed up as well. So the question is, how or does this process really exist? I mean, what about the optical properties of the ice? Can we really make something like a spider in the lab? So can we really make this absorbing layer to produce so much ice that it cracks the ice, and actually some of the dust that is in this absorbing layer escapes with the gas over pressure? And I've got this fantastic marvel of technology here. So this is what is going to happen in our experiments. What you're seeing here is a sample that is about 12 centimeters in diameter. It's about 12 to 14 centimeters high, and it's a block of clear carbon dioxide ice. Carbon dioxide ice we can make in the lab. It requires obviously carbon dioxide gas and very cold temperatures. And what is inside this block of carbon dioxide is one of these absorbing layers. I mean, it's about like a 50p coin size little speckle of dust. So we've embedded like about a teaspoon of dust inside this thing. And then again, we seal this carbon dioxide ice block again. So you've got an absorbing layer of Mars simulant. Mars soil is not accessible, so we use simulant embedded in carbon dioxide ice, and then we shine the sun at it. So the sun is coming in from above, and this is inside the vacuum chamber. That means we've got Martian temperatures. We've got minus 120 degrees Celsius, and we've got 6 millibars carbon dioxide pressure. And let's take a look what happens. By the way, this cable, this is a temperature sensor that we've just embedded in this thing. And you can see the frost on the plate. The plate is actually what drives the low temperatures here. And as we see, the sun shines. Take a look at what's happening in the red square. And I don't know whether this is actually coming across over Zoom.
Yes, it is.
Yeah, brilliant. Okay. So in a while, you'll actually see that a little hole will open. There we go. And some black stuff you can see on the base plate. Can you see this?
Yes, it's quite clear.
Okay. Oh, fantastic. This is obviously a time lapse. Actually, you can see the time running in the top left corner. So this is a time lapse, I think, covering about like 8 hours or so. So we've effectively made the gas escape from our Mars polar cap, and thereby we have proven that actually this process works. I've got another video, but I don't think I've got enough time to show all the fancy videos that we've taken. So basically, this was the first proof of one of those theoretical models in the lab going, yes, we can do this. It is very, very sensitive, though, to environmental conditions. And that is an interesting thing, because the cryptic region is called cryptic because of these strange landforms. But people wonder, why is it only this region that is so cryptic? And you need to hit the very, very sensitive balance between the atmospheric carbon dioxide gas pressure and the temperature of the ice itself and the solar radiation. If you get any of these wrong, nothing happens. So it's really, really quite interesting, sort of just on the boundary of the equilibrium of the gas and the carbon dioxide ice. So really interesting physics going on. We've been to Mars, now moving on to ice in other places further out in the solar system. Comets 67P, and then 67P is possibly related to Kuiper belt objects, even though 67P is a short period comet. Now I put this slide in, even though I'm talking to an astronomy society, because I think it might be worth mentioning again. So comets, what are they? We distinguish between short period comets, with periods of less than 200 years. And then we've got the long period comets. And if you have followed the Rosetta mission, you will immediately have figured out that Rosetta looked at a short period comet. The origin of these two types of comet is likely to be a different region of the solar system. At least, they have spent a very, very different long part of their life in different regions of the solar system. Now, the reason why they become so spectacular is that they are likely to contain lots of frozen volatiles, that is ices. And I put this picture of Comet North in there, fantastic image, I think. And we describe them by basically the two tails they've got. There's got an iron tail, there's a dust tail, which means comets contain dust. Yeah, and we've got the coma that forms as the material in the nucleus sublimates under the solar illumination. And actually, this activity starts as the comet, which is usually on a very eccentric orbit, comes into the solar system and into proximity of the sun. And then, as it departs again and leaves to the outer region of the solar system, the comet becomes less active again. So this is driven by the tail formation is driven by the solar wind, and the coma formation is driven by the solar activity interaction with the volatiles and with the dust in the nucleus of the comet. Now, why are comets interesting? And that's because they are considered to be some kind of cosmic freezers. Our knowledge of comets has advanced dramatically even before Rosetta. Since I think the Rosetta mission, the first planning stages, like landing on a comet level, were already in the 1980s, I think. And since at that point, people thought comets to be very, very pristine, and they thought that comets contain a lot more ice than 67P did. But still, comets are very cold environments. They're very sort of unprocessed. So they're considered to be cosmic freezers, nevertheless, and even 67P was something that was fairly pristine. So, following the scientific method, so what do we actually know about comets, and how do we interpret that? We see the gas emissions with the gas tail, is dust tail. So we can tell from that comet nuclei obviously must consist of ice and dust, and dust can actually form these large and fluffy conglomerates that have been detected by some of the particle detectors, and I'll actually get onto that a bit later. So another thing that we see, and we remember that from the Giotto mission, was that comets have a dark surface. I mean, the Halley's comet, which was visited by the Giotto mission, very, very fast, almost kamikaze flyby, was a lot darker than expected. People thought, okay, comets must contain all this ice and dust. Surely they're not. They've got a fairly high albedo. It turned out, this thing is about as black as coal. So people then thought, okay, it must be lots of ice covered by a dust mantle, and this dust mantle is just the leftover dust of all the ice. From what we've seen with Rosetta, that isn't true either anymore. So, I mean, also we need to take into account that we now think of comets as not as distinct from other minor bodies in the solar system as we used to think. So another thing that we saw was, many years ago was I think it was end of the 1990s, was the Comet Shoemaker-Levy 9 breakup. This comet was disrupted as it entered the gravitational influence of Jupiter. And this one comet nucleus all of a sudden turned into this chain of little icy speckles that actually all developed their own activity. They all were in the same orbit. So from the comet breaking up just by the gravity of Jupiter, we concluded that the cohesion of these bodies must be fairly low. So they must be rather soft. So obviously, we needed a Comet mission to take a closer look, and that's how the ESA Rosetta mission came out. And if you excuse me for 5 minutes now, I will play you this not very scientific, but nevertheless rather entertaining and cute video that ESA has made. They've made an update, but that would be too long for this talk. So I hope the sound comes across okay with this.
Over 10 years had passed since Rosetta and Philae launched on their exciting mission to Comet 67P.
Is the sound okay?
Sounds fine, thank you.
Hang on. Okay, so we'll just carry on.
10 years had passed since Rosetta and Philae launched on their exciting mission to Comet 67P Churyumov-Gerasimenko. After 3 months investigating the comet from orbit, it was time to send Philae to its surface. A long night of final preparations lay ahead of them. Finally, the moment everyone had been waiting for arrived. As the world held its breath, Rosetta moved into the exact position needed to make sure Philae would reach the landing site that scientists on Earth had picked earlier in the mission. Philae and Rosetta were sad to be going their separate ways, but excited at the same time, because this is what they had been waiting to do. Philae was away. It would take 7 hours to reach the surface, but Philae wanted to get started on his measurements right away. He could soon see the surface in incredible detail, and the moment he had been dreaming of had finally arrived. He had reached the surface of the comet. But all was not right. His harpoons did not fire. Philae realized he couldn't relax yet. He was rising from the surface again. Philae was scared he might drift off the comet completely. This was not in the plan. But eventually, he came back down again. However, as he looked around, he realized he had landed in a completely unexpected location. Philae immediately set to work on studying his new home. It took him just over 2 days to conduct all the experiments he had brought with him. After all his hard work, Philae began to feel tired, so he made sure to send all the data he had collected back to Rosetta. As the sun set over Philae's new home, he fell into a deep sleep, safe in the knowledge that he did his main job well, and that his family of comet-chasing heroes would be proud of his achievement. Who knows, perhaps one day enough sunlight would fall on his new landing site and wake him up so that he could carry on investigating this incredible world. And so, as the comet moved over closer to the sun, Rosetta prepared for the next part of her exciting adventure.
Okay, now what I really like about this this animation is that it is historically and scientifically absolutely accurate. Each one of these actions actually has its counterpart in reality. If you like this, if you go into YouTube and search for ESA Once Upon a Time, you can actually find the summary of the entire mission that is about 20 minutes long. It's even cuter than this, but I don't have the time for that in my talk. On that note, actually, I've got a fluffy Rosetta toy, basically a fluffy Rosetta thing that is modeled after this animation in my office. So I'll now move on to the proper Rosetta, which is a lot bigger and a lot less cute. And I also am not all right with the idea that Philae was male in this animation to us in the control center. I think Philae was female. But anyway, so we've got lots of instruments on this mission. Rosetta was a spacecraft that had the wingspan with the solar panels of, I think, an Airbus 340 or 380, something like that. Little Philae is attached to the main spacecraft here. To give you something for scale, so this is the actual Rosetta spacecraft, and here you've got a random object in front of the Rosetta spacecraft. You can scale this. What we saw also was that the spacecraft actually, as it entered the orbit, it measured the comet's gravity, and thereby we could deduce that it must be very porous, because obviously if you compare the volume to the mass, then actually you get an idea of the density. So we deduced that the comet must be fairly porous. And we use that using radio science. And the reason why I'm showing this picture in that context is that at the time, actually before the launch, I was the radio science instrument manager at the University of Cologne. Another thing we concluded, as I said, this is Rosetta spacecraft. How big is it? Well, this random object is 178 centimeters in size. So you can get an idea of Rosetta spacecraft about 2 by 2 meters. Philae was a lot smaller, as you can see. I mean, Philae was is a box like on Zoom. You can't see my arm span, less than 1 meter by 1 meter, with this very, very complicated landing gear that turned out to have something to do with its fate on the comet, because this whole design did not quite work as envisaged. There's a number of instruments on this lander as well, and one of which was the so-called MUPUS probe, and that is basically a long stick, so a sort of pointy stick with a big hammer attached to it. And this hammer thing, I'll show you a picture later, is about as big as a Coke can. And then you had a drill on the lander, and you had various systems like these 2 harpoons that were supposed to fire and hold it to the ground, which didn't work. This spacecraft, again, cost millions, and effectively we were very, very lucky that it returned some data. Now, the taxpayers certainly got their taxpayers' value for money, because we got 3 landings for the price of 1. Because, the lander tried to descend onto the surface, then the thrusters that were supposed to hold it to the comet at this very low gravity environment had to be deactivated because there was a problem with the pressure. These harpoons then didn't fire, so it immediately went off into space again. And we were at the time quite worried that actually it might never come down ever again. But however, it did hit a rock, about an hour later. And then it bounced off again, and then it went into a different direction and eventually came to rest. Now, that was obviously not as it was planned. And you've seen from the previous picture of the lander that actually it is very sensitive to the attitude it has on the surface. It's like with three legs basically up in the air, it's not going to measure very much. So as I said, this animation was historically very, very accurate, because here you can see little Rosetta bouncing off a rock. And from that, we can again deduce comets must be hard. Now, hang on a minute. I mean, just before we said comets must be soft because they break up so easily. So again, you see some kind of, is it a dichotomy? Is it just a contradiction? Is this comet very, very different? So you can see that actually Rosetta then opened up lots of cans of worms in terms of new knowledge that needs to be gained. And this hammer thing that I talked about is an instrument that was developed by DLR, which is the German Aerospace Agency in Berlin, Space Center Warsaw. Other institutions were involved in that as well. It was deployed from the Philae lander using an extendable arm. So basically, there was this deployment device here, and this thing could then be deployed at a distance of almost 1 meter from the lander itself. And it was designed to autonomously hammer itself down into the surface, because it has these barbs here at the tip, and there's this little Coke can-sized hammer. And you can adjust the energy per stroke of the hammer. And thereby, you could actually then measure the progress, and that will give you hardness. And on the day, this is the image that we got. So you see time here, so on the horizontal axis, and the position of the Coke can above the surface. So this is effectively a time series. We just keep measuring the distance of the Coke can above the surface of the comet. And what you can see is that there is almost no change. Like it just wobbles about as the hammer tries to propel this thing into the surface. Now, since the whole system was designed to work in microgravity, it is impossible that the hammer did not hit anything. It just was bouncing about in mid space. But actually, what we see from this is that obviously it must have hit something, and whatever it hit must have been very, very hard. Now, a lot harder than the design specifications of the hammer, which again, you saw the previous image, so it was historically accurate, little Philae with breaking its hammer. So that was a lot harder. Here we go. Where's Philae breaking his hammer? So we deduced from that comets must be really, really hard. I mean, not only bounce off hard, but break a hammer hard. Again, contradicts with the previous observations of comets breaking up easily. So there have been comet simulations in the past. The last big sort of campaign was in the 1980s, early 1990s. Technology has moved on since then. So we try to do something, because we do ice simulations, we try to do something very, very similar. We try to just put water ice, fluffy water ice that meets the porosity criteria of this comet, contaminate it with some dirt into the vacuum chamber, and this time pump it down to space conditions. So really, I mean, in vacuum, then shine the sun at it and see what happens. That's what we thought would make sense. So we took a vacuum chamber, we took an artificial sun, we took our artificial snow, which we made in the lab, and the simplest possible contaminant we could think of was soot. So we just mixed snow and soot, and what we got is then something that is, almost white still. It has got a very, very high albedo. What happens is that as soon as you shine the sun at it, the surface sort of immediately gets darker. And if you shine the sun a bit longer, you will see that you get regions that are covered by dust. The dust sort of forms these conglomerates, or the soot, and the soot forms these conglomerates. And you put other regions that are completely white, where all the dust has disappeared. And the formation of these so dark and white region depends on the content of dust in your content of soot in your dirty ice sample. So we did various mixtures of soot and water ice, porous water ice, and basically just filmed the before and after. And actually, I've got a little animation as well of how this actually happens. So again, we've got a vacuum chamber. We've got a sample inside. This is the same size as the previous carbon dioxide ice sample. This time it's only water, ice, artificial snow, so very porous ice mixed with soot, carbon black to be accurate. And let's switch on the sun and see what happens. And you can see the surface gets dark, and then all of a sudden these little flecks of dusty stuff are basically blown away. Surface becomes white. And then you get the formation of these conglomerates of dark stuff on the surface. And you can actually see the level of the ice decreasing as more and more water sublimates in the vacuum chamber under the insulation. So you've got the formation of these dark regions and the white regions in between. What is really interesting about that is that we thought previously that comets are, or cometary surfaces consist of so-called active and inactive regions. And the active regions were rather dark, were rather bright, and the inactive regions were rather dark. Now, our current idea of comets is somewhat different, but on a micro scale, what we have produced here is effectively a model comet surface that has got a very, very dark region here, or has got lots of very, very dark regions, and some very bright regions, which are made of carbon dioxide ice. So to give you an idea of what happens, actually, this is the water ice surface before insolation, the scale here, and then you've got what the surface looks like after insolation, so insolation, so after the sun has shone at it. And you see these very, very large conglomerates of ice, of dust on top of the ice. What makes these conglomerates so interesting is that they, in a way, mirror what the particle detectors have seen. I mean, some of the dust detectors have some very fluffy material that obviously breaks apart very, very easily. And this stuff, actually, you can pick up with a spatula or a spoon, but it breaks apart. I mean, this effectively is just soot that has formed these long chains, and it's effectively held together by probably van der Waals forces. So in a way, we have reproduced something that is very, very similar to what we observe by spacecraft in conditions that are very, very similar to space. We're not sure whether this is the reality of what happens on a comet, but still we have sort of found experimental proof of what has been observed and say, hey, we can make this. So these models need not necessarily be totally wrong. And if you then look at what holds this stuff together, you actually feel how fluffy this material is. So this is a scanning electron microscope image of these fluffy particles, what they look like. And you can see that it's very fluffy, very, very low density. And you can see that actually these particles are held together by not very much in terms of contact areas. So we've seen this has been observed by spacecraft as well. And this is a bit of a geeky graph that I wanted to show you. I won't bore you with the physics of this, but actually if you then measure the hardness of this dark icy material after insolation, you will also find that the surface becomes a lot harder after the sun has shone at it, even though there's no melting going on. I mean, the ice in space conditions just sublimates. But we've also got a hardening, and we've got a sort of a sweet spot in terms of at which carbon addition or at which carbon contamination levels it becomes hardest. So we found that there is a sweet spot in terms of either absorbing the solar energy right at the surface and not letting much through, or basically not quite absorbing enough to harden the ice. And this is a process that is called sintering, where the ice just becomes very, very hard. Now, originally, this porous ice stuff, this artificial stuff, is very, very fluffy, and getting up to a hardness level of like 160 kilopascals, which is pretty hard. I mean, 160 kilopascals is almost as hard as say, a breeze block. So we're talking a substantial increase in hardness without any melting going on. And if you remember what we said about comets earlier, and how brittle they are, and how soft they must be, I mean, this is very, very soft material underneath, which has been processed by solar radiation and has become very, very hard. So in fact, we were also able to reproduce these local dichotomies, these local anomalies in terms of hardness, very, very hard surface, or in a material that is actually very, very soft. So again, we've shown that some of the models of comets need not necessarily be wrong. So that is one of the things that we've observed in our lab. If you look at then the imagery of the Comet 67P, this is very similar to what we see, only that the scales are very, very different. I mean, we're talking hundreds of meters here, and what you see before was less than millimeters in size. So we have been able to produce like sticky, fluffy dust particles that are very, very big, sort of clusters. We have been able to produce like gas that actually lifts gas drag that lifts dust off a comet off the surface, and we have also managed to produce hard ice. So we've ticked all the boxes that, yeah, but I mean, in a way, in the lab, we have been able to resolve all these seeming contradictions just by running the same processes that run in the solar system. We were quite surprised by that because there was so many strange things happening, particularly this dust stuff happening, and this has some relevance for Earth as well, and I will just briefly mention that later. Lots of questions arise in terms of the physics, which are still very, very poorly understood. I will take you a bit further from comets to, well, closer again, from comets to another type of minor body, which is asteroids. We've got asteroid Ryugu. That was the latest minor body visited by a space mission that I'm involved in. There was also Bennu, which was visited by the American OSIRIS-REx mission. The Japanese were faster though. And then we could possibly also talk a bit about Phobos. Now, why are asteroids interesting? In the past, we thought they are a distinct class of minor body. These days, we don't think so anymore. There's this continuum between asteroids and comets. And why are they interesting? And that's because they are also very, very primitive material, not quite as cold as comets, but still they offer insights into the early stages of the formation of the solar system. And this particular comet was very interesting because it's a C-type. This particular asteroid is because it's a C-type asteroid, which is very carbonaceous, very carbon-rich material, and that was something people were very interested in. The Japanese Hayabusa mission, I think I've forgotten to put in a timeline. Yes, but it was launched in the early 2000s. And what is really cool about the Hayabusa 2 mission is that the Japanese put lots of cameras on there. So you get lots of imagery of really cool stuff happening. For instance, I saw a time lapse of the autonomous navigation system, because we are so far out in the solar system, the spacecraft has to do all the navigation autonomously. And just seeing how the thing adjusts its position in order to get to the spot where it's supposed to go is just fantastic. Here's a selfie that the mission took of itself, as it was, against the sun. So this is Hayabusa 2's own shadow on the asteroid Ryugu. It also dumped a number of landers. One of them was led by, again, the German Aerospace Agency, and that landed on the surface and then flipped itself around because it landed on the wrong side. And that took also a picture, and that was a lot closer up than what we saw from the spacecraft. And you can see this, you've got this cauliflower-like structure on the surface. So even though this stuff looks like ordinary rock from far away, if you get very close, it is a lot more porous, a lot more brittle. It is very fragmented. It's sort of, this is not rock as we know it. We also found that the surface warms very quickly, and it cools very quickly. Now, if you take a brick, I mean, you might remember that in the olden days, people used to just put their bricks in the fireplace and then take the bricks out, as a sort of poor man's hot water bottle. That's because bricks are very solid, and they heat very slowly, they cool very slowly. This is a property is called thermal inertia. Now, this stuff has a very low thermal inertia, which means that it is not very dense. It is very brittle, it has lots of porosity, and it is not rock as we know it. So this is quite interesting in the overall context, because we wanted to explore a body that is very pristine. So taking this sample actually is very important for us, and actually also finding out the properties of this material in situ is very important for understanding this. So this is a quick rundown of Hayabusa 2. It was a very successful mission. We are now in the extended mission. The spacecraft is a lot smaller than Rosetta. It's just 600 kilos. It launched in 2014, arrived in June 2018, departed in 2019, and the sample was returned on the 5th of December 2020. Ryugu, the asteroid, looks like this. So it's got this strange shape that is caused by its spin state. You get this sort of a bulge near the equator, and it spins up. It's about 900 meters large in diameter, and it's got an orbital period of 1.3 years. And what makes it so interesting is that the fact that it's C-type, that means it's carbonaceous material. Hayabusa 2 dumped several rovers. It has a deployable camera, and it's got an impactor. It's got target markers, so that the mission was a bit like these. I don't know. I forgot what you call them. These transformers. Yes, these sort of children's toys that actually come from cars to robots and so on. Then launch rockets and missiles and all sorts of things. It's a bit like that, actually. It was a fantastic spacecraft, really good design. Built on the Hayabusa heritage, which was a mission that was a lot less successful, but still managed to bring a few milligrams of sample back. This is an overview of the mission. Again, lots of instruments, spectrometers, the usual suite of instruments. But what is really interesting is, in this context, the infrared and the landers, because they brought back the most interesting data I found. This is the mission timeline, very complicated trajectory to the asteroid, because there was no rocket available with sufficient mass for rocket propulsion. So this thing was actually ion propulsion, which means everything has to be done very slowly. It takes time, but still it was very successful, and all the ion engines are still working. Then what the mission did also was it launched an impactor that then impacted the surface on the asteroid, and made this crater. So we could take two samples, one on the surface and one in this crater. So to have the old surface material and pristine material from the inside of the asteroid. So first of all, there was a mapping, then there was the landers were deployed, then there was the sampling of ordinary surface, fresh surface, of ordinary surface, impact experiment, and then another sample taken. And it all went like clockwork. Mapping turned out that, Ryugu has got a very low density. If this is rock, for instance, that means porosity must be about 50%. Rotational state, it's retrograde, which was also rather odd. So we can deduce from that the rotational state must have evolved quite a lot since its formation. As I said, there was a whole armada of landers, and this image actually is possibly scientifically the most valuable because it shows the fine structure of the material, which is very brittle, very porous. This is the sample collection. It was a little horn that touched down on the surface, if you can see this through the video link. And then a projectile was fired, and the material that was then ejected was sampled by this horn, and it went into a little sampling chamber, which then was closed, and then another sample could be taken. It was all fully autonomous, so there was no telecombining. It was too far away. The round trip light time is too long for any commands from Earth. This is in a better frame of reference. Some amateur has actually processed this to give you an idea of the really, really complicated process that has gone on when the spacecraft found. So it autonomously descends, almost hits this rock, and then after firing a projectile, it autonomously ascends back into orbit once again, because it's so nice. Bang. Yeah, so sampling was successful. Then this impactor was released, and because it was too dangerous to film the impact, the spacecraft launched another autonomous camera to watch the impact while the spacecraft is on the other side of the asteroid. So a really, really cool mission. You can see the impact here, ejector curtain forming, fantastic, and spacecraft is not endangered in any way because the spacecraft is in a totally different place right now. So cool stuff. You can actually see, like in this blink image, what the crater looked like, and then the spacecraft went down to take some of the pristine material inside this crater. Also fantastic. And what's next? Well, 5th of December, the mission returned. You can see this little sample container that was dropped as the spacecraft flew by Earth. This then descended in Australia. During coronavirus times, it was a major logistical effort to get the Japanese team there to actually pick this up and then transfer it back to Japan. But it all worked perfectly well. And so we are now waiting for the sample analysis. You may have wondered what the science behind all this was, because I only talked about the cool technology. There's many discoveries about this asteroid that have all been published in Science and so on, so they are accessible. And we find that actually it has changed our view of asteroids, in particular regarding their porosity and the degree of processing the material as experienced. Now, since I am almost finished now, I talked a lot about ice and dust, like ice on comets, ice on Mars, and ice and dust or rock on asteroids. Why does it matter? Why do people devote their entire time researching this? And it's not only a bizarre and sort of obscure topic out of this world. It's actually something that is of very real relevance to what goes on Earth. I mean, you see these samples of what is effectively artificial snow contaminated with soot. Now, that is a material we find on Earth quite a lot, thanks to power plants, thanks to pollution. We've got the Greenland ice sheet, which is largely snow, although that's actually natural snow, and we've then got lots of pollutants coming in from particularly China that then contaminate the ice sheet on Greenland, for instance, and in the northern hemisphere. And the same thing is happening in the southern hemisphere. You get, for instance, contamination, albeit mainly dust from Chile that you find in the Antarctic ice sheet. Now that matters a lot because, as I showed before, you by adding these contaminants, you lower the albedo of the material. Now, and I pointed out at the very, very beginning of this talk that the albedo is essential for basically lowering the energy that we are actually absorbing from the sun and for controlling our climate. So the albedo of these ice sheets and understanding how the albedo affects the melting of these ice sheets, how the physical process happens, how the energy transfer happens when this stuff is contaminated, is something that is not out of this world. That is very, very relevant to what's happening on Earth. And to illustrate that, I've got this picture of a helicopter on the Greenland ice sheet, where you can actually see that the Greenland ice sheet is not white; it's almost black. So, and you can imagine, and you can see the meltwater here, you can imagine the massive effect that this contamination must have on the albedo and therefore on the melting of the ice sheet. And then sea level, albedo, you've got the sort of the feedback cycle that is happening. So it is massively important for us to understand how these processes happen. And in investigating these conditions in vacuum and in space conditions, we're just building the first steps towards actually understanding the physics of this. And thereby we can possibly become better at predicting what is going to happen next. However, that was a bit of a dreary note. The best form of ice cream in the ice in the solar system is actually ice cream in a cone in the sunshine and on Earth. So you also get lots of interesting flavors if you go to Scandinavia, by the way, like here. Okay, and that is my final slide, and I'm very, very happy to answer questions.
Thank you very much, Axel. Can you stop sharing your screen? Okay, and we have everybody back. Axel, that was a very informative and very interesting talk. Thank you very much. We are going to have questions now. Whilst people are just forming the questions in their own mind, when right back at the beginning of your talk, you mentioned the spider structures on Mars. And I came across a very interesting article on the BBC Science website regarding craters that are appearing in the permafrost in Siberia. And they think it's formed by expanding methane.
Yes.
And it struck me as being a very, very similar outcome. The process of getting the methane pressure up is different, but the outcome is very, very similar to what's happening on Mars.
Yes, it's interesting you should mention this. I mean, these spiders. I mean, the methane actually, it's mainly contained in the soil in the form of clathrates, as far as I remember. That means it is embedded in the ice in the permafrost. And as you raise the temperatures, of course, at some point it expands, and then these are the kind of things the kind of effects you get. It's interesting you mentioned that because I think it again shows the parallels between Earth and Mars in terms of investigating climate change and the effect of temperature differences or temperature increases on the processes, and thereby some fairly, I would say, catastrophic effects. Because I mean, these craters in Siberia forming, okay, we know there's lots of methane in there. Releasing all that again will start the feedback loop, because methane is a fantastically productive greenhouse gas as well. It's very effective. It's almost as effective as water, I think. And by the way, carbon dioxide, well, we all talk about a lot as a greenhouse gas, but water is a lot more effective as well as a greenhouse gas. So these massive feedback cycles that are becoming apparent as we investigate these processes a bit more, I think it's not only interesting, but it is scary, because you find you're doing planetary science, or you're doing planetary research, but in the end, because of the parallels to what's going on Earth, and because of the I think urgency of tackling all these processes, I think all of a sudden you find yourself in a position where you can contribute, or where you need to contribute to something that is very, very important. I mean, scarily important. I think these craters in Siberia, actually, in a way they highlight how important it is to understand these processes in other worlds as well.
Okay, thank you. Ladies and gentlemen, I'm looking for questions. As usual, I would prefer if you put a digital hand up, but if you can't manage to find the reactions button on the bottom of your screens, wave at me. But be warned, I am having to scan through several screens. So, over to you. Questions. Catherine, can you unmute yourself, please?
Right.
Evening, Catherine. Can we have your question, please?
Good evening. Has anybody been able to replicate the formation of organic molecules in asteroids and comets?
Very good question. Not. There have been, I think, some experiments on, I think, amino acids. I'm not sure what the current state of that is. Those are scales that are beyond my realm of experience.
Yeah. Thank you very much.
Okay, thank you, Catherine.
Yes, yes.
Anybody else for a question? Phil, can you unmute yourself, please?
Yeah, hi Axel. Lovely talk, really interesting. Yeah, when you were describing how comets are formed, I think of them as a bit like terminal moraine, where you get deposits collecting, where you might have big pieces of rock, and then you get lots of small particles gluing it all together. So you end up with a big mass, but it's soft and it's also hard at the same time. That's how I envisage comets and asteroids as much as anything else. And I think the only difference is the fact that as comets come close to the sun, it's blowing the dust away, and then it's picking it up when it's going back out into the outer solar system. Whereas your asteroids are more or less the same distance away from the sun all the time, so they're not blowing away the dust like comets do. So that's my take on it.
Yeah, thank you. That's interesting.
Thank you.
There is a difference, though, in terms of composition, because asteroids contain almost, or contain very, very little volatiles, whereas comets contain lots of volatiles, obviously. So in terms of the region of formation, they are, I think, from different parts. Plus, I mean, there's this whole variety of different asteroids as well. You've got, for instance, material that is probably a lot harder. You've got monolithic asteroids, and sorry, I'm rambling on. But one of the things that I find quite interesting about the asteroid observations we made with Hayabusa 2 was that the material that seems to be so fluffy that a lot of the meteorites, so we think that the C-type meteorites that we find on Earth, the carbonaceous chondrites, they are representative of these asteroids. But from the infrared data, we deduced that the material that is on that comet is so fluffy that it would not survive atmospheric entry. That means we have no analog for this material that has been brought back by Hayabusa 2 on Earth, even though we thought previously that this is one of the parent bodies of these meteorites. So I think over the next decades or couple of decades, I think there's going to be lots of interesting discoveries to be made on this whole asteroid-comet continuum and how to put things together, because we now know that the meteorites that we find on Earth, were thought to be linked to this type of asteroid, but now we know that is not true, or is unlikely to be true.
Interesting. Do you think asteroids are made in specific parts of the solar system and move around, or are they forming and staying in the same place in the solar system?
Well, I think that's unlikely, and But again, you need to ask somebody who does orbit modeling. I mean, we like 4.6 billion years is an awfully long time, so you can do lots of things with orbits in that thing. But what is obvious is that there are different types of asteroids simply because the composition is so different, and there must be different target bodies, different parent bodies of them. I mean, you've obviously got stuff that used to be sort of a planetesimal core. We've obviously got material that used to be sort of a planetesimal crust or mantle, and we've got stuff that is very poorly processed. That is in the process of actually forming a core and a mantle. So the sort of early stages of the differentiation of a pre-planetary body or proto-planetary planetesimal. So that is, I think, something you need to keep in mind when you speak about different types or different origins of these bodies, because obviously there are different types. They must have come from different parent bodies.
Thanks very much.
Thank you. Tony Morris, can you unmute your microphone, please? Evening, Tony. Can we have your question, please?
Hi, Axel. I was just wondering about as the comets move through the solar system, especially the short period ones, they will go through heating and cooling as they pass close to the sun away. Has there any thought been given to how that affects the surface morphology?
Yes. That depends. Well, first of all, it depends on, I think, a number of factors in terms of the interior buildup and the morphology to start with. I mean, the 67P comet, for instance, you've seen this bilobate shape that I showed in one of the images, actually in the cartoon, because also it became quite obvious. Now, we think that quite possibly this bilobate structure is caused by the fact that these used to be two different bodies to start with. And they then basically just started off just being gravitationally attracted, somehow merged together. And now you've got these two different bodies with two different lobes, or head and a body, which then rotate, and they probably have different composition, which means that then the surfaces are processed in a different way, and the erosion happens in a different way. And the morphology of the two surfaces is also very, very different. Another thing about the morphology changes as this very, very complex, or geometrically very, very complicated structure then orbits the sun, is that the strange lighting conditions, then the very, very different interior, actually that leads to this sort of what has been likened to an onion shell structure. You've got plates of material just being blown away. And then you've got these steep cliffs, and as the volatiles within these steep cliffs then are exposed to the sun, you then get cliff erosion. Because gravity is so low, this takes quite a while, and also the stuff then drops very, very slowly and then rolls very, very slowly on the surface. So the getting closer to the sun and moving away triggers a chain of morphological changes that are, in a way, very, very diverse. So you've got something that looks like a cliff face, but what produced it in the first place, it's effectively like mass wasting, but that's only because the cliff was exposed very, very quickly in the first place. So it's the getting close and then moving away that triggers the surface changes to start with. Does that answer your question?
Yeah, it does. Could I come back? You actually described the close-up view of the surface of a cauliflower-like structure. Mm-hmm. Well, I think I've seen in books where they say cauliflower follows like a fractal pattern distribution. So is there any inference there using cauliflower to how the surface builds with maybe the particles' shapes and sizes?
I think the cauliflower came about by probably somebody just having had cauliflower the night before. It's just that it resembles cauliflower. Maybe somebody else has spotted it, they would have said it looks like broccoli. But the that is literally what the surface was likened to by a colleague. The fractal structure or the fractal nature, I don't. Well, we haven't really seen enough of it to be able to tell. And right now, there's the early stages of investigation of the samples that have been taken, and the colleagues investigating those samples in the lab, I think they are probably still in the curation facility. So I don't think they have even been released for research. They are looking at that, and then we're doing X-ray spectroscopy to actually X-ray tomography to actually find out what the interior structure of these things is. There'll be a lot of porosity at many different levels. That is the conclusion so far. So fractal structure, yeah, I mean, different. We're talking various very, very large scales and very, very small random processes. Yeah.
Okay, thank you.
Just going back to the sample return mission, Axel, once the sample is on Earth, won't some of the physical properties actually change?
Yeah.
Because you're immediately bringing something from deep space back to Earth, back to standard pressure and temperatures, etc.
Sorry.
No, carry on. That was it, really.
Okay. Yes. But with this particular sample, the Japanese Space Agency took great care to actually avoid contamination and all that. So, for instance, the samples were delivered back to Earth in vacuum containers. The first thing that JAXA did in Australia was actually because all vacuum seals start leaking after a while, was try to extract the residual gases inside these little sample chambers before they even picked up the sample and then take it to Japan. And then the samples or the containers were opened under vacuum conditions. Again, gas extraction happened. Then the material is being investigated for now under vacuum conditions. And before any of the stuff will be released and actually be shipped somewhere, so most of the investigations go on under vacuum conditions. Still, I mean, the stuff has seen atmospheric entry into Earth. I mean, that is not going to be easy business for a fluffy fractal structure. So it's likely to be mechanically altered just by atmospheric entry. The sampling process itself has changed the material, because you remember, this is effectively the ejector from an impact of a projectile. So the very, very fluffy stuff is very likely to have been destroyed.
Okay.
Yeah.
Right. I'm still looking for people with questions. I am Peter Lloyd. Would you like to unmute yourself, Peter? Hello, Peter.
Yes.
You have a question, please.
Yeah. Thank you, Axel. I just wanted to follow up slightly on that last question, because I tend to get intrigued by the engineering, and this might therefore be an unfair question to you. But when they came to picking up this sample, yes, they fire a projectile into the comet and it throws bits and pieces out all over the place. They didn't just have an open box and hope some of it went in and didn't come out again. I mean, if there was any air around, you'd suck it in, but you obviously can't do that. I mean, was it just chance that stuff went into the box and stayed there?
Yes, effectively, yes. I mean, that is a valid question, I think. The asteroid sampling mechanism, because there was this massive funnel that was supposed to channel it into the box, that was the way it worked. But they never had the expectation of getting the entire sample container filled, because they knew it's a random process. You're collecting ejecta that are bouncing around a giant trumpet, effectively, like this funnel. They were very, very lucky to actually get as much sample material as they did get. I think the mission requirement was, I think, 0.1 something grams. I don't know. That was the expectation, and actually they got, I think, 5.4 grams home. Now, for cosmochemical analysis, that is a load of material. However, when they opened one of the sample containers, actually there was also a piece of aluminium that was quite probably part of the whole funnel thing. That was not supposed to be there. But since there's so much material, actually, nobody really cares because it's massive. On that note, the American mission to asteroid Bennu, I mean OSIRIS-REx, they've got a massive hoover. They just basically have this gas jet that blows material, like it blows into the surface, and they've got this massive sort of thing that then sucks up the material. So effectively, you know, hoover mechanism.
You may not have air, but you can take the air with you. Yes, I understand. Thank you.
Thank you, Peter. And we will go back to Catherine, please.
As the formation of asteroids and comets and things is poorly understood for bodies up to 10 meters, could ice be used in the formation of these things? Because instead of having like two bodies coming together and they bounce off, if you had ice on the surface or snow or even fluffy stuff, it would come together and stick. Do you think that might be useful?
Well, ice as glue has been proposed by a few people. I like that idea. I know this colleague working on asteroids who has been trying to explain cohesion of asteroids. He likes the idea of ice as glue. There is no evidence though. The question also is how effective it will be in deep space conditions, because I mean ice in these conditions, like in the outer solar system, is ice because it doesn't evaporate. But what you're saying is something that people are thinking about. Yeah, the main reason for these bodies sticking together is probably gravity. Van der Waals forces probably play a role as well. And then you're looking for possibly some other agent that acts as a glue, and ice, you know, is being looked at as one of them as well.
Thank you.
Okay. Ladies and gents, I think we have worked Axel hard enough this evening. So we'll just give our usual Bexper and Swinton Astronomical Society thank you to Axel. Axel, thank you for a very entertaining and informative meeting.
Thank you very much. It's been a pleasure.